Good afternoon. Now this is the example number 5th and video number 6. So in this example, in this video, we'll see how to do the analysis of a portal frame using stiffness matrix method. So on a screen, you are seeing one portal frame. So it has a two elements. BC is a beam element and AB is a column element. AB is subjected to uniformly distributed load and BC is subjected to a point load of 100 kilonewton, which is acting at the center of the span. Now, since the C support is the hinge support, so therefore lateral sway is not possible. Lateral sway because of this lateral loading is not possible because this is a hinge support. And since because of this, since C support is a hinge, lateral displacement is not possible. Therefore, this frame is a non-sway type. So in the case of analysis of the portal frames using stiffness matrix or any other method, first of all, it is very much important is that we must be able to recognize whether it is a sway type frame or it is a non-sway type frame. If it is a sway type frame is there, then analysis is something different. And if it is a non-sway is there, then analysis is different. Now this is a non-sway type. Now the analysis of the non-sway frame and analysis of the continuous beam. So the steps are absolutely the same. There is no change. Okay, so first of all, develop the displacement matrix, then generate the load matrix, then generate the stiffness matrix, then use equilibrium equation, then determine the unknown displacement, and after that using slope diffraction equation determine the final end moments and then plot the bending moment diagram as we have discussed the steps in the previous videos. Now, first of all, we'll generate the displacement matrix. It is delta matrix. To develop the displacement matrix, determine its kinematic indeterminacy. So this is our basic structure. So this support is a fixed support. This is a fixed support. So therefore, degree of freedom will be equal to 0. Now this is the joint, rigid joint is there for a 2D frame. So the degree of freedom at this particular B joint is a 1. That is a rotational degree of freedom. So theta B is the unknown displacement at coordinate B. And C support, it is a hinge support. So at the hinge support, only one displacement is possible. That is a rotational displacement. So therefore, in the structure, there are two unknown displacement. Both are rotation displacement. First is at B support, theta B is the 1, and second at C, it is a theta C is number 2. Then assign the coordinate. We'll call this unknown displacement as a 1 and this unknown displacement as 2. Then write the displacement matrix. So displacement matrix will be equal to, this is the first coordinate, unknown displacement is theta B at B point, and this is the second element at coordinate 2. This is unknown displacement at C point, that is theta C. Call this equation number 1. Second, now to generate the load matrix. Now to generate the load matrix, determine the friction moments. Okay, so friction moments are because of the external loading. Now open, actually this frame is a, okay, so this frame is like this and it is subjected to UDL. This is subjected to UDL and this is subjected to a point load. And here there is a support C. Okay, now to calculate the friction moments, okay, you just open the frame. Okay, so open the frame in the sense whatever the column A to B, rotate in an anti-clockwise direction. Why anti-clockwise? So that this UDL will act in the downward direction and make it as a beam. So this is AB, just for time being, you just make it as a beam. The load is acting from the downward, and then calculate the friction moments. So assume this support and this support as a fixed beam, have a fixed supports, so that AB will be a fixed beam subjected to UDL. So this friction moment will be equal to WL square by 12. It is standard formula, it is hogging nature, and this will again, it is WL square by 12. It is hogging nature. Then next is B to C. Okay, B to C, assume this as a fixed beam subjected to point load. Then fixed beam subjected to point load. This will be hogging bending moment, this hogging nature. And what is the fixed end moments? It is WL by 8. This is WL by 8, and CB will be equal to WL by 8. So these are the fixed end moment or restraining moment due to loading at the ends of the supports or the members. Then write the load matrix. Now the load matrix, there will be two elements. So this is the first element. So this is the first element at our first coordinate is at B point. So at B point, what are the restraining movements are there? So 150 is a clockwise, plus use plus sign. So 150 minus 62.5. So it will be equal to 87.5. And this is coordinate number 2. So coordinate number 2 is again clockwise, and it is a 62.5. So these are the two elements in the load matrix. Call this equation number 2. Then generate the third matrix, stiffness matrix. Then the size of the matrix will, there are two coordinates. Okay, there are two coordinates. Therefore, size of the matrix will be equal to 2 by 2. This is wrong. This is not 1 by 1. It is a 2 by 2 matrix. Now to generate the first column of the stiffness matrix, apply unit deformation at coordinate 1. Okay, now this is our frame. This is our frame, and this is the coordinate number 1. This is the coordinate number 1. Coordinate number 1 is a movement which is a clockwise movement. So at B support, apply the clockwise movement. Okay, so B is common to both spans. So both span will deform. So this will deform in a downward direction. Beam will deform in downward direction. Then because of this clockwise movement, this will be going to deform in this way. Then this unit deformation, that is again how much movement is required to apply. Whatever we are applying this movement, how much movement, so that the slope at B point will be equal to 1. Then this unit deformation, when it is applied at support B, it will create the moments at the ends. Okay, so calculate these end moments by drawing each element free body diagram separately. So this is a beam BC portion. So here this moment is acting clockwise from the top, right? So this will deform downward. Then to produce this slope will be equal to 1. This slope equals to 1, that is theta b equal to 1. How much movement is required to apply here? It will be equal to 4 EI by length of this member. So you call this member as L1 length and this beam as a L2. So 4 EI by L2. And at the far end, how much movement will produce? It will be equal to half of this, half of the 4 EI by L2. So it is 2 EI by L2. So these are the moments in the portion BC. Now portion AB Portion AB is deformed in an outward direction. So the slope, this slope will be must be equal to 1. So how much movement at the support B? It is 4 EI by L1. And how much movement at the far end? It will be equal to 2 EI by L1. So these are the restraining moment developed at the ends because of the unit deformation. Again, apart from this, the reactions at the ends of the member also develop. But in the figure, these reactions are not shown. The reason is that our coordinate 1 and coordinate number 2 both are movements. Therefore, in the stiffness matrix, both elements are the rotational forces. Okay, so therefore, the reaction are not required in the stiffness matrix. The reactions are not coming in the stiffness matrix. Therefore, unnecessary do not increase the time for solving. That particular calculation which is not required, don't do it. Only the moments are required. Therefore, the moments are shown in the figure. Then from these two figures, we can write the elements of the first column. The first is K11, stiffness at 1 due to unit deformation at coordinate 1. So stiffness at 1 in the sense at coordinate 1, that is at B point, what is the total rotational force? Okay, so total rotational force, this is in the element AB, and this is element BC. Okay, both are clockwise. These two forces are in the direction of assigned coordinate 1. So therefore, both elements will be positive. So 4 EI by L1, and this is 4 EI upon L2, and EI value for BC portion is 4 EI. Okay, then substitute here. So the first element is coming as a 3.86. Then stiffness at 2 now. Stiffness at 2 due to unit deformation at coordinate 1. So stiffness at 2 in the sense our coordinate 2 is at a C point. So at C point, what is this thing? Rotational force, it is 2 EI upon L2. Okay, so it is plus, it is a clockwise. Okay, so this is a clockwise and our assigned coordinate 2 is also clockwise. Therefore, this element is positive. So 2 into EI value is 4 EI divided by L2 is 5 meter. So it is coming 1.68. So this is the first column of the stiffness matrix. Then generate the second column of the stiffness matrix. So to generate the second column of the stiffness matrix, apply unit deformation at coordinate 2. Then coordinate 2 is point C. Coordinate 2 is a point C. So apply here clockwise moment because our coordinate 2 is a clockwise. So then provide fixity also. Before applying the this moment, we have to provide the fixity. So when the moment is applied here, only BC portion will deform in upward direction as shown in the figure. So apply the moment so that this slope will be equal to 1. Then this unit deformation at C point at coordinate 2 will produce the end moments in the beam portion in the second part only. So in the column portion, no moments will be there. Now in the beam portion, here, this is a clockwise moment is applied. Okay, slow that this slope will be equal to 1. That is unit deformation must be equal to 1. So how much moment required? It is 4 EI by L2. How much moment produced at the far end? It is equals to 2 EI by L2. Okay, then the first coordinate will be stiffness at 1. Stiffness at coordinate 1. So this is our coordinate 1. So what is the moment produced? It is equals to 2 EI upon L2. So 2 EI value is 4 EI divided by 5 meter. So it is equals to 1.6 EI. Then K22, stiffness at 2 now. Stiffness at 2 due to unit deformation at 2. So coordinate 2 is here. This point is coordinate 2. So it is clockwise. Our coordinate 2 is also clockwise. So therefore it is positive. Element is positive. So it is 4 EI by L2. So 4 EI value is 4 EI divided by 5. So it is equals to 3.2 EI. So this is the second element. And then our required stiffness matrix is shown in equation number 3. Then equation 1, 2, 3 connect by using equilibrium equation. So it is a load matrix plus stiffness matrix into delta matrix equal to 0. So load matrix equation number 2, this is stiffness matrix equation number 3 into displacement matrix is equation number 1 equal to 0. Then do the multiplication of K matrix and delta matrix and then write this matrix form into equation form. So we get this equation. Okay, and determine the unknown. So the theta B and theta C. Okay, so both answers are negative. Both answers are negative. So it means that our assumption regarding the rotation at B and C are wrong. Here, what is the assumption we have made? This unknown displacement at theta B we have assumed as a clockwise. So theta B we have assumed as a clockwise. Theta C also we have assumed as a clockwise. But the answers are coming to be negative in the sense our assumption is wrong. So these slopes are not clockwise, but these slopes are anti-clockwise. Then once the values of the rotations are calculated, once the rotation values are calculated, then by using slope deflection equation, calculate the end moments. Calculate the end moments or calculate the final moments. So using slope deflection equation. So this is the slope diffraction equation for AB span, then BA span. Okay, so here EI into theta B, already it is determined, substitute value as it is, minus 18.40. These are the end moments, friction moments due to the external loading. So already in step number 2, while generating the load matrix, we have calculated this. So take the value along with the sign as it is. Okay, so here in this video, this that is detailed explanation of the slope deflection equation is not a scope, beyond the scope. So therefore, I am not explaining in this, because it is assumed that the students are well aware about the writing slope deflection equations. Then this is MBC. Okay, since C is a hinge support, we can use a modified slope deflection equation. So these are the answers along with the nature, whether it is sagging or hogging nature. And then finally, after getting the answers, final end moments, then plot the bending moment diagram. Okay, so this is the bending moment diagram for the example. So this completes the, and then this completes the this example. Then in the continuation, I will explain the next example also. So this is again a T-shape portal frame. Again, it is a non-sway type. This is non-sway type because there are two reasons. First is A support is a hinge support, and therefore the frame will not move in a lateral direction. And C support is a fixed support. So therefore there is a lateral restraints are there. And therefore the frame is not allowed to move in a lateral direction. So it becomes a non-sway type. Once it is clear whether it is sway or non-sway, then immediately start the analysis. So since it is a non-sway, the analysis is similar to continuous beam. So you just consider BD as a one more continuous span. So this is D support. Just like a continuous beam, do the analysis. So in the first step, develop the displacement matrix. Displacement matrix. So displacement matrix, the unknown displacements will be at A support and at B support. Okay, so this is fixed support. The slope will be 0. So here the rotation, unknown displacement rotation will be equal to theta A, and this is theta B. We will assume both as a clockwise. Okay, both as a clockwise. So degree of freedom of this structure is 2. Okay, so what are those? Rotation at A and rotation at B. Now, okay, so this is a, now we can write the displacement matrix. So this is the first element. The first element is at coordinate 1, that is at A. So what is unknown displacement? Theta A. And at B, what is unknown displacement is equals to theta B. So call this equation number 1. Then next is to develop the load matrix. Now to develop the load matrix, assume each span as the fixed beam, and because of the loading, what are the end moments? Just calculate this. So this is a fixed beam. This is the first is, it is subjected to UDL. A, B, C, it is subjected to UDL, and lateral load is there on a column B to D. Okay, so assume this as a fixed beam, AB as a fixed beam subjected to UDL. So this fixed end moment will be anti-clockwise direction, W L square by 12. Length is known, W is known. So at B support, it is W L square by 12. Then for BC portion, again, there is a UDL. So this is anti-clockwise WL square by 12. And this is again anti-clockwise WL square by 12. Both are hogging nature. Then about the column now. Okay, rotate the column and make it as a B. Okay, so how to rotate? Now the load is acting from this direction. So rotate in such a way that load should act in the downward direction, similar to beam. So I have to rotate in an anti-clockwise direction. So rotate in this direction, anti-clockwise direction. So it will become a fixed beam. So this will be support B. Okay, so this will support B and this will support D. And it is subjected to the load here. Okay, so from D support, the distance is 2 meters. This is 2 meter and this is equals to 4 meter. 4 meter, right? So here then, what is this moment at B support? So it will be anti-clockwise as shown here. This is anti-clockwise, and what is the value? So it is fixed beam subjected to load eccentric. So this value will be equal to WAB square by L square. WA is 4 meter, B is 2 meter. So WA into B into AB square, A into B square divided by L square. Okay, and this moment will be a clockwise moment. This will be clockwise moment. So what is this value? WA square B divided by L square. Okay, so these are the answers. End moments. Okay, so all fixed moments are after determination of this, we can write the load matrix. Now here, first in this step itself, calculate all the fixed moments acting which are there at the ends of the support, because these values are also required while writing the slope diffraction equation. So therefore, calculate these values, all the values at this particular step itself. Then this is the load matrix. Now next we'll go for the next matrix, that is the stiffness matrix. Okay, now before that, just I forgot to explain this load matrix. Now this load matrix are, okay, now this is the first element. No, this is the first element. So it is coordinate number 1. So here, this is the, what is the restraining force? So it is anti-clockwise, therefore minus 37.5. And this is at coordinate 2. Coordinate 2 is at the B point. Now at B point, there are 3 moments. There are 3 moments. Use plus sign for clockwise. So it is 37.5 minus 150 minus 11.11. So total is minus 123.61. Call this equation number 2nd. Then generate the stiffness matrix. Okay, now there are 2 coordinates, therefore size of the matrix will be 2 by 2. Now to generate the first column of the stiffness matrix, apply unit deformation at coordinate 1. Now this is the basic structure. So apply fixity here. Apply fixity at this particular point first of all. Okay, and then apply the moment at coordinate 1. Okay, how much moment? This moment should be, this slope must be equal to 1. Okay, so since we have provided fixity here, so only the span AB will deform. Okay, and this deformation will create a end moments. So these are the end moments shown separately, free body diagram. So here this slope equal to 1. How much moment required to apply? 4 EI by L1. L1 is this, L2 is this, and L3 is the length of the column. So 4 EI by L1, at the far end it will be equal to half, 2 EI by L1. Okay, then K11, stiffness 11. Okay, our coordinate 1 is a moment now. Coordinate 1, this coordinate 1 is a moment. So at coordinate 1, what is the moment produced? How much moment is, this is coordinate 1. It is 4 EI by L1. So it is equals to 1.33 EI. This is stiffness at 2 now. Okay. Force, rotational force at coordinate 2 now. Now coordinate 2 is at B point. How much it is? Clockwise now. 2 EI by L1. So 2 EI by 3. So it will be equal to 0.67 EI. So this is the first column. Then to generate the second column of the stiffness matrix, apply unit deformation at coordinate 2 now. Okay, now coordinate 2 is B point, which is common for 3 span. So BC, BA, and BD all will deform. So this is the deformation shown in all the columns, or column and beams. Deformation in all the members. Okay, and how much this moment to be applied? How this moment to be applied? In the clockwise, because coordinate 2 is a clockwise. Okay, and then how much moment to be applied? Magnitude should be such that it should produce slope equal to 1, theta b equal to 1. Then draw this deformed shape separately. This is for AB portion, this is for BC portion, and this is for BD portion. Now the point where the moment is applied, at that point it will be, moment will be equal to 4 EI by L1. at the far end it will be equal to 2 EI by L1. So this is the point where the moment is applied. At that point, moment will be 4 EI by L2. At the far end, it is 2 EI by L2. For BD portion, this is the point where the moment is applied. At that part, at that point, it is 4 EI by L3. At the far end, it is equals to 2 EI by L3. Okay, so these are the end moments developed. Okay, then write the stiffness matrix. Okay, the first element is K1, 2. Stiffness at 1 now. Stiffness at coordinate 1. Okay, what is coordinate 1 is here. This is coordinate 1 at A point. Okay, so what is the moment? Clockwise is there. It is a clockwise, and our coordinate 1 is also clockwise. So it is in the same direction, therefore element will be positive. How much it is? 2 EI by L1. Okay, 2 EI by L1. So L1 is 3 meter. So element is coming 0.67. Then K22. Okay, now this is a K22 means at the point B. Now here there are 3 moments are there and all are clockwise. Okay, so this is movement second, and this is the third. All are clockwise, that is in the same direction as that of the assigned coordinate 2. Coordinate 2 is also clockwise. So therefore, just take the addition, signs of each element will be positive. So this is for 4 EI by L1 for AB portion. This is for BC portion, and this is for BD portion, whose moment of inertia is equals to 3I. Okay, so right here. So in all, after addition, it is coming 4 EI. Then these are the second, these are the elements in the second column. Then write the stiffness matrix. This is the first column and this is the second column. Now, after this thing, after developing stiffness matrix, equation 3, just check it whether it is correct or not. Apply the properties. We know that the stiffness matrix is a square matrix. So here, this is there are 2 rows and 2 columns. The first properties is this thing is satisfied. Second, it is a symmetric matrix. So this element, it is a, what is the position? It is K21. 21 equal to 1, 2. Okay, so both are same. It is stiffness matrix is a symmetric matrix. So these elements must be same. And third is that the element lying in the leading diagonal always must be positive. So this is the leading diagonal. So these elements must be positive. So yes, it is correct stiffness matrix. Then go for the next step. Then use the equilibrium equation to connect the 3 matrices. So load matrix plus stiffness matrix into delta matrix equal to 0. So this is load matrix from equation step number 2. Equation number 2, this is a stiffness matrix. Equation number 3, write as it is. And this is displacement matrix. Equation number 1, write as it is equal to 0. Then do this multiplication and then take this particular on the right side. So it will change the sign of these values. So we get these 2 simultaneous equations. Solve these 2 simultaneous equations. We get the unknown displacement at A and B are 13.19, 90, and 28.57. Okay, both values are positive. It means that these are, our assumption is correct. What assumption made here? At A point and at B point, the unknown displacements are clockwise. Rotation at A and rotation at B are clockwise. This is the assumption made, and the answers are also positive. That means our assumptions are correct. So slope at A and B are correct. Then after knowing the value of theta A, theta B, then by using the slope deflection equation, determine the final end moments. Okay, so this is for MBA, use modified slope deflection equation. So this is MBC. This is MBC, use a general slope deflection equation, MCB. So here MBC, MCB values are nothing but fixed moments due to the external loading. So which already we have calculated in step number 2. So enter the value along with the sign. Then for BD portion again, that is column portion, it is use a general slope deflection equation. And then and then after knowing the final end moments value and their the nature, sagging, hogging, then plot the bending moment diagram. So this is the bending moment diagram finally it is. Okay, so by using stiffness matrix approach. And again, you can check the results by solving the same example either by using either by using moment distribution method or by using the slope diffraction equations. In this example, we have used slope diffraction equation, but where it is used to calculate only the final moments. Otherwise, the unknown displacements are determined by using the stiffness matrix approach. And then once the theta values are known, then we don't have other option to find the final moments except using slope diffraction equations. So therefore, check the answer by solving the same example by moment distribution. Already I have checked it, so the answers are matching. Okay, so this is the end of this example. So up to this, we have discussed the portal frame of a non-sway type. In previous videos, we have discussed about the continuous B with different conditions. That is varying moment of inertia. There is sinking of the support. Overhang is there. Okay, how to do the analysis using the stiffness matrix approach. Okay, so thank you. In the next video, we'll discuss about the portal frames with sway type.